What happens when you train a state-of-the-art diffusion model on a dataset that's fundamentally flawed? Specifically, what if the vast majority of your training data is noisy, containing artifacts from sensor noise, compression, or low-light captures? In a perfect world, we just curate a clean dataset. But in the real world, high-quality, manually verified data is expensive and rare. Most large-scale corpora are heterogeneous and messy. When a diffusion model is trained on this kind of mixed data, it doesn't just ignore the noise. It learns the noisy distribution as the dominant mode. The result is that your generated images inherit those high-frequency artifacts, significantly degrading the output quality. Today, we're looking at a new paper from Kyushu University that proposes a clever solution to this problem. It's called SDEdit, Spectral Cutoff Regeneration. The most impressive part: it's a training-free, generation-time method. You don't need to retrain your model or fine-tune it. You simply change how you sample from the model you already have. To understand why SDEdit works, we first have to look at the spectral bias of diffusion models. In the frequency domain, the semantic structure of an image, the big shapes and primary colors, is captured by low-frequency components. Undesired noise, however, lives almost exclusively in the high-frequency bands. Crucially, diffusion models exhibit a specific behavior during the reverse process. They tend to infer high-frequency details based on the low-frequency cues already present. If the model was trained on noisy data, it uses those low-frequency cues to hallucinate high-frequency noise, because that's what it saw during training. SDEdit intervenes at the sampling stage to break this cycle. Instead of just accepting the noisy output of a standard diffusion process, SDEdit applies a frequency cutoff. It essentially applies a low-pass filter to the generated image, wiping out the corrupted high-frequency components and leaving only the clean, low-frequency structural information. But a low-pass filtered image looks blurry. To fix this, the researchers use SDEdit. SDEdit is an image editing framework where you take an existing image, add a specific amount of noise back into it to move it backwards into the diffusion process, and then run the reverse denoising process again to regenerate the details. Now here is the technical core of the paper, the mapping between the cutoff frequency and the SDEdit initialization time step. If you add too much noise during the SDEdit phase, you destroy the low-frequency structure you wanted to keep. If you add too little, you don't give the model enough room to overwrite the original noisy artifacts. The authors solve this by using radially averaged power spectral density, or RAPSD. By analyzing the RAPSD of the diffusion process, they define the signal-to-noise ratio, or SNR, at a specific frequency and time step. They identify a crossover point where the signal power equals the noise power. By setting the SDEdit initialization time step, which we'll call T', to the exact point where the SNR of the cutoff frequency is equal to 1, they create a theoretical boundary. This ensures that the regeneration process starts from a state that is mathematically optimized to preserve the signal, while regenerating the high-frequency details according to the models prior. The researchers tested this on two fronts: synthetic noise using CIFAR10 and real-world noise using the SDEdit dataset. In the synthetic tests, they used a mix where 90% of the training data was noisy, either Gaussian, Poisson, or a mix of both. When comparing SDEdit to standard diffusion models, bilateral filters, and even noise-robust GANs like NRGAN, SDEdit consistently won. In terms of FID scores, which measure how close the generated distribution is to the real clean distribution, SDEdit outperformed everything. What's particularly interesting is the robustness. Even when the cutoff frequency wasn't perfectly tuned, SDEdit still significantly beat the baselines. They also tested varying the ratio of noisy data from 10% up to 90%. While standard diffusion models saw a linear collapse in quality as the noise increased, SDEdit remained remarkably stable. Moving to the SDEdit dataset, which features complex real-world smartphone camera noise, the results were even more telling. Real-world noise is signal-dependent and much harder to filter than simple Gaussian noise. Traditional post-processing like bilateral filtering actually made the FID scores worse because it blurred the image without actually removing the complex noise. NRGAN struggled because it couldn't accurately model the real-world noise distribution. SDEdit, however, managed to produce clean, high-fidelity images because it doesn't try to model the noise. It simply removes the corrupted frequencies and lets the diffusion prior fill in the blanks. To wrap up, SDEdit provides a powerful blueprint for dealing with contaminated training sets. By leveraging the spectral properties of diffusion models and using RAPSD to mathematically determine the optimal regeneration point, we can recover clean images from models that were trained on dirty data. It turns a fundamental weakness of the training process into a sampling time strength, all without the massive computational cost of retraining. If you're working with large-scale, uncurated datasets, this is a technique worth implementing.